Hi everyone. Hello. Are you guys sitting?
All right, folks, quickly, if you're coming, come on, settle foot quickly. We're about to start the session. Let's go. Cyril, can we ensure everyone in the back is seated?
Or
Yeah,
it's fine. It's fine. It's fine.
perfect.
Hi everyone. It's been a great afternoon. The topic for the conversation would be understanding proof systems. Ideally, I'll be going over what is proof systems, how do we construct those proof systems. So ultimately, by the end of this session, you should ideally have enough points to go over and get an understanding in more depth. So I'll be probably covering a bit of a width in this session. So as we go along, feel free to tell me if you have any questions. Okay. So hi, I'm Abix. I am currently contributing at Zisk. Zisk is a ZK VM that is being built currently. X Polygon developer editions. Moving on to starting from the point. What we'll be covering in this session is basically basics of proof systems, models of proof systems plus cryptography equals to snarks and starks. That has been like a round of conversation around the state. What is your knowledge from starks, snarks to ZK snarks and ZK starks to how, where are they being used? So basics of proof systems. So in order to basically start even before understanding what proof systems are, let's go on to brief understanding of what proofs are. So at the core, a proof is a logical demonstration that confirms a statement is true. So think of it as like showing a proof of work that says, for example, let's consider the same example. That's it. So you're considering, let's say, a series of numbers, and you're saying that you know the hash of the particular series, and where h is publicly known as a hash. So proof is the reasoning that basically convinces that I know the input without revealing it directly. So in order to basically consider the fundamentals of a proof system, proofs are a fundamental part of it. So think of it as more like they're kind of answers to a reasoning path. So, okay, so that's a pretty deep diagram to work with, right? That's a very brisk of an ideology when you basically say that you have a ZK proving system or a proof system. There are multiple components involved in building that proof system. So ideally, if you break down any proof systems, there are fundamental frameworks or objectives that can be listed down. So these are some of the key framework or points that are there in a proof system. So axioms, so consider them as like the foundational statement and a truth that are accepted without any prior truth or proof. So if we take an example of such thing, this could be, let's say, 0 is a natural number, or things that are fundamentally true and do not require a pre-proof to start with. Next is formal language. So this is more like the grammar we use to work alongside or like present or build up a proof system. So using equations like a equals to 2k plus 1 is equals to odd. So like any odd number is basically a composition of 2k plus 1. So you basically representing that statement into a format. Consider it more like a grammar for writing proof systems. So what are inference rules? So inference rules are basically, let's say, the rules that take axioms or like build up on top of the pre-fundamental truths. So if, let's say, we are evaluating or like building up a proof system, so this diagram potentially has all of them, but it would be pretty complicated if we went down this route. So, but if you can see, all of these components are potentially used to eventually come up to a foundation of building a proof system. That's ideally fundamental for any proof systems that you go along. So any of the proof system that you evaluate, work around, learn, will have these foundationals of the proof systems to be built upon. Then proof derivation, the step-by-step path that we potentially follow. So if you see the last segment of it, the potential path that we followed during the combination of, let's say, considering formal language, axioms, and inference rules to build up a more sound and completeness of that proof system. Soundness and completeness are two very broad topic when we consider or like build up on top of like soundness or on like ZK systems or like proving systems itself. So if a system says something is proven, then it's really true. So soundness potentially verifies or like states that if a system is saying something, it's potentially true to state of inputs. Completeness is something that is true, that the system has a way of tracing back to it or proving it again. So summarizing it up pretty quickly, a proof is basically a formal argument that derives on the statement based on axioms. So you're basically deriving on the fundamental truths that are based out of, let's say, a collection of inference rules, proof derivation, soundness, completeness, and that's what like a combination of systems would together fundamentally bring you to that part. Okay, now that was a quick speed run. Now moving on to the second part would be models of a proof systems. So ideally I'll be covering these 4 quick models to give you a fundamental idea of like what are the different kind of proof models that are there and how they eventually work along. So to start with, let's start with interactive proof. So the framework or like, let's say, consider for a foundation that you need to prove that you have a result for A plus B equals to C. Interactive proof generation system basically relies on the part of verifier and the prover interacting with each other and coming up with a variability that the proof is valid. Right. Non-interactive proof systems are basically proof systems that generate a proof that verifier can check without any back and forth for the communications to be built upon. So in this case, let's take an example where Alice knows a secret number A, B, and A plus B equals to C. So answering on the fundamentals of it, there would be no communication between Alice and Bob to validate the resultants of it. There are ways where this can potentially be converted into an interactive proof generation system. There are things like Fiat Shamir and more. So basically there are a possibility as you go further to learn along the conversations of like why things are being converted from, let's say, a type of a proof system plus cryptography to reach a resultant state of snarks or stacks. Next would be probabilistic checkable proofs. So let's say the proof size is very big, right? You have a computationally heavy proof and you want to prove it very fast. So how do you do it? You basically take like, rather than proving the complete proof, you basically take few parts of it and they still convince the higher probability of the proof being true. So it's basically, I would say, working on more like a randomness plus oracle fundamental, where you take up parts of the proof and verify the validity of that proof rather than working through the complete one. IOPs, these are the kind of proving systems that basically combine the back and forth communication part and the oracle system. So let's consider for a fact that it's basically more like a hybrid system that is designed to make like heavier proof verification pretty fast. So we basically are working on an oracle query or like working on data sets of that proof plus the combination of like interactiveness from the verifier and the prover. Okay. The reason we're skipping fast is basically to move on to the next topic for ZK. Okay. So ideally, the foundation of like proving systems or the model systems to be built along was to move towards less interaction and more efficiency so that we could ideally achieve a more faster and a privacy-focused proof systems to be attained. There are multiple combinations that are used to basically work and generate snarks and stacks. So if potentially I had to basically explain on a very abbreviate level what snarks and stacks would be, so consider it more like proof systems plus cryptography equals to snarks and stacks. So any kind of proof systems that you might consider between the four, plus a state of cryptography, could result you on a hypothetical basis of building a snarks and stacks. So you would potentially see like a different standpoint of like combination of using a particular cryptography scheme plus using a kind of a proving system to end up with a resultant recipe of like similar snark, similar plong or groth with different combinations of work or proof systems to be attained. Okay, so proof systems are basically designed to guarantee the soundness and completeness of the proof being true. Cryptographic tools help us to basically fix things to prove this without revealing the fundamentals of it. So ideally, the combination gives us different kind of proving systems that would be on the lines of different kind of snarks and stacks. There are various kinds of individual snarks and stacks potentially to work with. You might have already heard about Groth 16. You might have heard about implementation of stacks with different kind of FRA implementations. So consider it on the fundamental level. It's ideally you're utilizing a proof system plus a state of cryptography to resulting it into a state of a particular proof that is being driven. So I think we can skip this. So yeah, let's think from this particular idealistic perspective. Each system is basically built by a combination of like proof systems plus frameworks. So like in this, if you see PCPs or like IOPs with specific cryptographic hashes based upon commitment schemes, and different choices or trade-offs would lead us to a different state of verification cost, set up arguments or like post-quantum security and things. So that's like basically you can think utilizing proof systems plus a state of cryptography would be a variability of choices for you to choose upon and ultimately result upon like what are the trade-offs for each. Individuals or like individual schemes and their choices would result into different trade-offs and assumptions to be worked upon. So that's why the combination basically helps us to attain the similar kind of schemes and resultant metrics to have systems like Plonk, Marlin, Starks, all with different variations of it. Okay, so these are few of the cryptographic mechanisms that are available, or like most recognized one that are being utilized to build these proof systems. This is a slide from Risk Zero, so you can potentially go and dive a bit more deeper into it. But yeah, so we had a quick speed run on understanding like a brief about how proof systems are, what proof systems do, and how we eventually came up to a formation of utilizing proof systems with cryptography to bring up the foundation of snarks and stacks. Now, the proof systems give us like a structure of proving and verifying. Cryptography gives us the foundation of a primitive that's like hashing, algebraic tools, and other frameworks to make it concrete. Together, they produce like efficient proof systems, such as like snarks and stacks. But efficiency is not that whole story. Ideally, it's basically on the format of utilizing the state to come to a foundation of not sharing the witness data and having a certain state of proof being generated utilizing different proof systems and cryptographic schemes. So let's move on to understanding what zero knowledge is. So on a very low level understanding of basis, you can understand zero knowledge basically means that you are proving something that is true without giving any extra information. That's like a very basic of an understanding. To give you an example, let's say you solved a Rubik's Cube or a Sudoku puzzle. Ideally, you don't have to share the numbers in the puzzle, Sudoku puzzle, rather sharing the verifier, the validity that you already solved it. So it's basically abstracting on the fundamentals of not revealing the initial solution of it, but rather a proof of the solution being true. what are zero knowledge proofs? So let's combine the fundamentals of proof and zero knowledge to basically construct a foundation where we can eventually say that a proof driven from a certain state of inference rules derived to a particular parameters combined with a certain set of cryptography eventually results up to a sound or a concrete proof. While that proof is being true, you'll also need to basically introduce a part of zero knowledge to it. So the reason we do it is basically in this case would be, so let's say there could be multiple reasons for you to do it. In this case, it potentially accrues down to you not sharing the secret of that proof generation. You're not sharing the witness of that proof generation, rather the validity of the claim of that proof being true. Okay, so we were able to identify the space coming from like proof systems, cryptography, to ending up to snarks and stacks. ZK snarks and ZK stacks are basically an extension to the construction of those proof systems alongside cryptography, alongside the state and the foundation of zero knowledge, to basically abstract on the information for witness generation or keys to basically have a fundamental proof of validity. So the proof in this case, or like the key difference is that's basically around the lines of like moving from snark stacks to ZK snarks and ZK stacks. It's often I would say, represented, where we often use it more rigorously on the part of like swapping terms. It's basically the proof is constructed so that the verifier learns nothing but the fact that that statement is true. So you're basically working with the combination of proof systems, cryptography, and this foundation to build up such a snarks or a stack to prove that thing. So yeah, one of the examples how a ZK snark, or like a foundation, a brief example how you can think of building a snark is basically representing back from like the proving system fundamentals would definitely come from different state of accumulations of axioms, inference rules, and cryptography choices to result up into the choice or the resultant metrics for like proving systems. Where are these proof systems being used currently? So one of the prominent places where they are being used is ZK VMs. So it's basically a combination of both, in this case, snarks and stacks. So potentially work with different accumulation of proving systems to end up with a foundation result that's more accountable for a single proof. So this is an example from RISC-V ZK VM. So it's eventually using a combination of both snarks and stacks to get up with like a single state proof that is easy to verify and prove. So yeah, that's it from me. Thanks for having me. Thanks.